I looked at in the first kind of 2/3 of my time doing a PhD. And so Alex suggested me this problem, and so I'm thankful for that. It's a very nice problem. So, yeah, and some of you might have heard me give similar talks. So I'm going to skip over, I'm just going to write down, state the general setup, state some theorems, skip over a lot of stuff very quickly, and then I'm going to try and talk about something, well, that I think is quite interesting to do with this. So I have Q. Be a quadratic form. That's going to be rational. So that means it's got rational coefficients, or it's a multiple of a form of rational coefficient. Indefinite, non-degenerate. Take M. This is going to be a linear map. So here the LI's are linear forms. And I'm going to take a rational number such that this set so this is just the integral solutions to this equation, and I want to choose this A so that there are going to be infinitely many of them. Okay. So then first theorem. So this condition, so all D to be bigger than 2s. Oh, one more notation. So I'm going to, this is quadratic form. I'm just going to denote this quadratic form by Q sub m. Okay. And so I want Q sub m to be indefinite, and the rank of Q sub m to be at least 2. I want the following conditions. So for all alpha in RS. Non-rational. So this is a rationality condition on the linear map. So provided these conditions hold, I can say that M so the image of all these integral points on the surface is going to be dense in the image of the linear map M. Okay, so I'm not really going to explain. Well, I'm just going to say a few things about it. So, I want to say a few things about these conditions. So, this condition 1 is too strong. Probably. Well, I don't know for sure that it's too strong, but I would conjecture that it's too strong. Should probably be something like S should be less than D minus 2 or equal to D minus 2, possibly, so that one. These conditions too, so the fact that Qm is indefinite, this implies that if you look at the set X, Q, R intersection so here might be in RS. So it implies that this set is going to be non-compact. Okay, and this condition is a necessary one. But yeah, possibly this one is too strong.
Sorry, could you say again what condition 3 says?
Condition which one?
Condition 3.
3. So it says that any linear combination of these linear forms is not a rational form, so it means it's not a multiple of a rational form. Okay. Okay, so yeah, this condition is actually needed for the conclusion. Is that okay?
Is the letter in 3 is x? Is it x?
Yes.
Nice x?
Oh, this one.
Yes, yes.
Alpha, yeah.
Alpha, sorry.
Yeah, and, well, X if you want. But.
Okay.
Okay. Yeah, and obviously you need condition 3 as well, because without this condition, then even if you just look at just ZD, the image of ZD, then it may not be dense. So, okay. So, what do I want to say? I think I just want to say, yeah, I want to just say kind of this sort of setup. So, dynamics. You take G to be equal to SOQ connected component, gamma equal G intersection SLDZ, H to be equal to the stabilizer in G of M. So because Q is rational, this one is a lattice. And, well, then we can act on, yeah, we can act, so we can let H act on G mod gamma, okay? So, right, this condition 2, right, so this is something you can check. So 2 implies that H is generated by one parameter unipotent subgroups. Okay? So that's why you need this condition 2. So in this case, so it's, yeah, I guess not too hard to show this, but that's what it does. And then, well, then you can use Ratner. So Ratner then implies for all x in G mod gamma, if you look at the closure, the H orbit, this is equal to fx. So for some closed connected subgroup of G, which is containing H. Okay, so then the problem is, well, you just need to show that this subgroup F that you get is big enough. So that's where you need condition 1 and 3. And you can use these to show that F equals G. And then after you've done that, the theorem follows. So this bit's kind of quite straightforward. This bit is, I'd say, more difficult. And yeah, that's why I need this condition D bigger than 2s. And I don't really know a good way of doing it. I think there's probably a better way of doing it, which would mean that you didn't need that condition. Yeah.
What is H? What does it mean to stabilize M?
So it means that the set of G in G such that M G X and X for all X. Okay, so yeah, that's just how that's what kind of all I really want to say about this. So that's kind of how you do it. So then I want to say, well, so there's you could prove an improvement of this theorem. So yeah, let's just call it theorem B. Okay, so condition 1 is going to be the same. I'm going to change this. So I want, so the rank of Q sub M to be equal to D minus S, and the signature of QM to be equal to PQ with P at least 3 and Q at least 1. And then condition 3 is the same. Then conclusion is different. So this is like an equidistribution version of so it's density result. So then for all R in RS compact, boundary, we have the following asymptotic, so it's the limit t tends to infinity of the size of the set x in xq g such that mx is in R and has bounded norm. Over the volume, the real points. So the same set, but I just replace z with R. Okay, and so this volume, oh, well, I haven't said what it equals. That equals 1. Yeah, this volume on the bottom is the volume, so the invariant measure on this surface. And you can show that, well, this, what I've got on the bottom, write it, let's see. Star. So then star is going to be asymptotic to some constant which depends on Q and M volume of R t to the t minus s minus 2, which is what you, well, so yes. Yeah, and this is Lebesgue measure, the s-dimensional Lebesgue measure of R. Okay, so the proof of this is based on work of Eskin, Margulis, Moses from '98, so where they did quantitative Oppenheim, so proof based on the '98. And so the philosophy is that, so in theorem A, we used orbit closure theorem. The philosophy is, well, to get this kind of theorem, you replace orbit closure theorem by equidistribution theorem. So what is the equidistribution theorem I actually want to use here? It's, okay, so I take, so, well, let me first define like a function. So f is going to be a continuously compactly supported function on Rd. And then I define, so this is like the Siegel transform. So I'm going to define a map from G mod gamma into R. And this is going to be defined by summing over the point, well, the integral points in the surface. So it's the sum over x in x, q, z, f of g, x. Okay? So this is the type of function we would like to apply some sort of equidistribution.
Sorry, that's the Euclidean one?
This one here. Yes. Yeah. Yeah, actually, I mean, it's not too important about which norm you take there.
So it's not important that it's K invariant?
No, I think you can just, here, you could replace this by just any kind of like smooth, sort of convex, kind of growing, expanding kind of shell. And things. I didn't actually work all the details out, but I think it should still work. Okay, so yeah, you define, yeah, like analog of Siegel transform, and this is the kind of thing you want to apply the equidistribution theorem to. And the problem you sort of run into is that this thing is unbounded function. So you need to, well, yeah, it causes problems. So, so I'm going to write down the equidistribution theorem that I actually use. So this is, so you take AT going to be one parameter subgroup of H such that there's this row. It's going to be a continuous homomorphism from SL2R onto H, such that with continuous homomorph with row of the diagonal equaling A. Should I call that A? No. Okay, so, and then again, what K is going to be equal to the maximal compact subgroup of H. And then the equidistribution theorem is, so lemma, or, yeah. If you look at the average of K, so F hat ATK d nu. So this is the Haar measure on K, this measure nu, well, it's supposed to be a nu. If you look at the limit as t tends to infinity, this is equal to the integral on G mod gamma d nu. So here, this is the Haar measure on G mod gamma. Okay, so bear in mind, so that there's rationality conditions hidden in what I'm saying here, because the G, yeah, everything. This is the stabilizer of rational quadratic form, and here K is the maximal subgroup of the stabilizer of the irrational linear form. So there's kind of rationality conditions hidden in this statement. So yeah, it's kind of specific to this situation. I think you could actually prove this kind of statement in more generality if you wanted to. And and this side is actually equal, so this is like some constant which depends on Q times the integral over the surface. I've missed out there. This is F hat F D XQ. So okay, so this is well, you need to use this relation as well. So this is kind of an analog of Siegel integral formula in this setup. So how can you? So this lemma. It follows from sort of two things, really. So there's a result of Danny and Margulis proved in 1993, so their paper where they established lower bounds for the quantitative Oppenheim conjecture. So it follows from an equidistribution result that they proved there. So Danny and Margulis 93, and non-divergence estimate. For this function f hat. And so that estimate is, what you need to show is sub t bigger than 0 integral over k. So this is exactly the strategy that was used by Eskin, Margulis, Moses. This is the kind of point where things diverge a little bit and get so you need to show this type of bound. Okay, so how would you do that? Well, so in order to do that, so you define, say, some operator. So you define, for H in H, and F is going to be some function on H. So R, you define operator, so AT, FH, the integral of a K, F, AT, K, H, d mu K. And then you say that, so, definition, F is contracted by AT if, so for all C bigger than 0, there exists T naught bigger than 0 and B bigger than 0, such that A T naught F H is less than C F H plus B. Such that, for all H. Okay, so because, so the part of this which is to do with contraction is the fact that you need it for any, you can do this for any C bigger than 0. And so then there's a lemma, there's a lemma which you can use. So this is from, it says that F from H to R is continuous left K invariant. And you want to, F should be finite at these identities, and F is contracted by AT. Then if you look at the supremum of AT F1, this is less than infinity. So you can see, so this is kind of what we want to show. Well, so this is the operator. So we just need to kind of construct some function F. So we need, what properties do we want it to have? We want it to satisfy all of these properties, and we also need it to be, so if we have like alpha, well, I messed up. Okay, I've done something in the wrong order, so let me define something else. Okay, so I'll take delta to be a lattice in RD, and define the function alpha of delta is going to be the maximum, and also, so omega I delta is going to be the set of U1 wedge UI, such that U1 up to UI elements of delta. So this is a subset. Here, and then it's going to be the maximum over the union of I. So U in 1 over the norm of U. Okay, so this function kind of measures how close to infinity you are in the space of lattices. So if this lattice has short vectors, then this thing is going to be big. But even if it has small, say, two-dimensional subspaces, because each thing, so imagine this I is 1, then you're just looking at one-dimensional subspaces which intersect the lattice if I is 2, you're looking at the co-volumes of two-dimensional subspaces which intersect the lattice. So it measures, kind of how close you are to the cusp. And it has the property, so there's lemma of, so this Schmidt, which is from around, which says that, so alpha, f hat g is going to be less than some constant which depends on f, alpha g for all g in g mod gamma. Okay, so I can think about alpha applied to an element of g mod gamma by first embedding g mod gamma in SLDR mod SLDZ, and then using the usual identification with SLDR mod SLDZ with space of lattices. So what this means is I can prove this non-divergence estimate with I can think about the alpha instead of the original function that I had. Okay, so and then so what I wanted to say was, so what we need, so in view of this lemma and this, so if we can find some fh, well we want f a function from h into r such that say alpha h, I've missed out something. Here there should be some delta. Okay, this is quite important. So here I want delta to be bigger than 1. Yeah, the delta being bigger than 1 is kind of what actually enables you to prove the equidistribution result that you need to prove. So if it was just 1, you wouldn't actually be able to, it wouldn't work. Okay, so you need it to satisfy all of and lemma. Is satisfied. Okay, so how do you build? Well, so how do you? Yeah, so I mean, we could just use like some linear combination of the alphas. So this is kind of what is used in the paper of Eskimogoulis Moses. Essentially, they're using like linear combinations of averages of the alpha function for this function f. And so then the hard part, well, the bit that takes some work is to show that this function is then contracted by this operator at. And so what you need to do to show that this function is contracted by the operator at, you need to estimate. So you need estimates of the following form. So you need, for all c bigger than 0, so exists t naught greater than naught, such that for all v in some wedge, if you look at the spherical average, the integral over k, 1 over 80 k v, this should be less than c. Okay, so you need this kind of estimate. So once you have this kind of estimate, you're sort of in business. But so this is not going to work. The problem is this doesn't work when h has fixed vectors. So so the reason for that, so if h has fixed vectors, does The reason being is that v can be very close to being fixed, but not fixed. So in that case, the norm of v can be very large, but it could still be very close to being fixed. And in that case, when you act on it with the AT, which is kind of, well, it's going to be kind of expanding it. So it's what's going to give you this shrinking. But the bit that AT is acting on is very small, the norm of it, so it can't grow it that much compared, and because the V can be arbitrarily big, so yeah, the norm of V can be arbitrarily big compared to the norm of the bit which AT is acting on. So you can't prove this kind of uniform statement if H has fixed vectors. Because the kind of thing is you need it to hold for all V in here. So if there are fixed vectors of H in here, it doesn't work. So what that means is you need to replace the norm by some other function, which kind of doesn't care so much about the fixed vectors. So this, so the function you actually should use here is one. So it's a definition defined by Benoit and Kant. So this is definition due to okay, so they define a function which you can use to replace this norm here. And so yeah, so I've still got the definition of alpha written down. Yeah, so you can see in the definition of the alpha function is depending on the norm. So if you just replace this norm, this 1 over the norm, by some other function, you can define an equivalent to the alpha function. You keep the maximum the same. So what you need to do, you need to define some function on these wedge products. And so that's exactly what they did. So how is it defined? You take rho to be the representation of H in the exterior power. Okay, and you let P, this is going to be the set of highest weights of the irreducible subreps. Okay, so yeah, because H is semi-simple, it decomposes into some of irreducible sub-representations. Each one of them has highest weight assigned to it, and so you just say P is the set of all of those highest weights. And then you say for lambda, and P U lambda is the sum of all reps with highest weight lambda. Okay, so that's just collecting together all of the representations which have the same weight. And then you define the projection, which is the projection from the exterior algebra onto the collection of these representations. Okay, then you put them for V in, oh, and I want to set gamma I to I times D minus I. So then for a vector in here and epsilon bigger than 0, you define that's the minimum of a lambda in here So the representation with weight 0 is that's just the trivial representation, so that corresponds to the fixed vectors. So U0 is the fixed vectors of H. So here you're taking the minimum over things which aren't fixed. So here, if the projection onto the fixed vectors is small, you do this. And then it's 0 if not. Okay, so why is this function better for us than the norm?
Can you just repeat what is tau x or lambda?
Tau lambda, so it's a projection from here onto
Okay,
onto the sum of representations.
I have a dummy question. What is the weight of representation?
So the weights are like the weights. So they're essentially you look at the roots. So there's what am I saying?
Okay, you have this application from growth to linear space. And how can
Yeah, so the weights are essentially like the eigenvalues. So you have the adjoint representation, and you look at you look at the eigenspaces, and then you can order them. So and
for diagonal group, you look on diagonal group, and eigenspaces for the eigenvalues for diagonal group, and then we look in the highest.
there's some ordering.
Yeah, but why have you told that for trivial representation when everything goes to zero-dimensional space? Oh, okay.
Yeah. Okay, so why is this function better? Well, so there's kind of a couple of important things. So one thing is it's equal to infinity in the case that so V is H invariant, and the norm of V. Well, this is just the norm of V in this case, but it's less than epsilon to the gamma I. Okay, so this is important, and also, well, so if it's not equal to 0 for some V, then you can subtract the fixed part without changing it. Okay, so this is kind of crucial. And is there anything else I wanted to say about that? No. Okay, so because of this, so have I still got estimate? Yeah, so this type of estimate here, right? It's this part here is essentially defining a norm on the complement of the fixed vectors. So it's just like a weighted average of norms. So you can prove this type of result for the vectors in the orthogonal complement of the fixed vectors. Okay, so that's going to be, so if you take this to be your norm on that space, then you can still prove this type of average. And because of this, then it doesn't matter if the vector where you start with is not in the orthogonal complement of the fixed vectors, because you can subtract this part and then it is. So you just stretch it.
Where is T here, TTV? Where is T on right?
Sorry?
V sub T of V.
Here.
No, the definition is
Price of t. So what is t?
Oh, it's a phi sub epsilon.
This is a phi. Yes, epsilon. Sorry, am I right? Bad. Yeah. So all of these things that look like t's are epsilon. Okay. So that's kind of why this function is better, because yeah, you can just work in the orthogonal complement of the fixed vectors, and then you can prove this contraction, and then everything is kind of working out for you in kind of much the same way as it should do.
So what do you do with norm in place of norm?
So yeah, I'm going to explain that bit now. So what you do, well, maybe I should keep that. So you can define f epsilon delta to be the maximum of the U in this union. Just all you do here is put C epsilon U. Okay, so you just literally replace this with this one. Okay, and so then there's a couple of things you need to check. So one, well, this can be infinity, right? So if this vector is H invariant, then we could just get something. This can be infinity, but that would be bad. So we have to check. So well, this, right, you've got to remember this delta here. So if delta is going to be corresponding to the one we actually want to consider, is going to be corresponding to the pair, the quadratic form and the linear form. So, and then if, simplify if U is in Pi delta, U is not H fixed. Okay, so this is going to be some finite thing. Okay, so this isn't too hard to check, so it just follows from the ration. You've got this, remember the rationality condition, no linear combination of the linear forms is rational. It means that inside some subspace there's no rational subspaces, and then you can show that implies this. And what else do you need to check? Well, it's no good. So we know that the function that we actually want to consider, the function that we're actually interested in is the f hat. And we said we could replace the f hat with the alpha function. But, well, maybe this doesn't have the same property of bounding it, so we also need to check that.
You mean this function f epsilon is analogous of this alpha?
Yeah, that's what I'm trying to tell you.
What do you mean when passed from alpha to this epsilon?
Well, so that's, yeah, it kind of, because you have basically this is the kind of really key point, because the fixed vectors were causing us problems. So this means that I can subtract, so I take away the projection onto the fixed vectors from this. This is now in the orthogonal complement of the fixed vectors, so I can work with this instead of this. Okay, so that's kind of, this is the advantage that I have using this.
You mean you work on a projection? You want to work on a projection to a subspace instead of ordinal?
Yeah, this is like the projection to the orthogonal complement.
But why not just introduce norms which measure only the size of the projection and not of all the data?
Yeah, I mean, you can try and do this, but then it still, if it's a norm on your whole space, it doesn't work, because no matter how you try and, well, maybe I tried for quite a while.
It will be same norm, of course, but
Yeah, I tried for some time to get that kind of thing to work, and it didn't seem to work. This really seems to make everything work out and be not too bad. So maybe there is another way.
I think he's doing the same thing, right? So, but he has to say that the things that are close to this subspace which is bad can be controlled, and this is what he's saying.
Yeah,
okay.
yeah. Because the trouble is, if you don't have something like this, then it can still be very close to being fixed. And when it's very close to being fixed, no matter how you define the norm, it's still it can still be big in the other direction. Like as a whole, the whole vector can still be big. It can be as close as you want to being fixed. And it causes problems.
You want certain distance from
Yeah, essentially, yeah. You need to kind of say, okay, well, I only care about things.
Thank you. I have one more technical, very stupid question, but I really don't understand it. How to 0 can be different from 0?
Hmm?
Because if it is, you told that the representation of height weight 0 is just a trivial representation.
Yeah.
It's not every single trivial
Yeah.
space. So highest weight is 0 as far as.
Yeah, the highest weight of the trivial representation is 0.
Yeah. Then to 0 is simply you map.
It's the projection onto the
your
fixed vectors.
multi-vector to 0.
No, it's a projection onto the fixed vectors.
Constant.
On
Fixed vectors.
Fixed vectors. Yeah, the trivial
so
representation is
everything-
mapping everything to the
okay.
identity. So it's
Okay.
yeah. Okay. Oh yeah, so the other thing I want to check is, well, I can claim that alpha delta, well, it's equal to the maximum over, let's just call this omega delta. So u in omega delta with tau naught u less than epsilon to the gamma I plus maximum. But I want to say less than u. Okay, so I just write it like this, and then here, well, you can just bound it straightforward bound by epsilon to the minus gamma, right? Here and here. Well, in this scenario, this thing, because this is just like a weighted average of norms, there's going to be some constant which depends on epsilon here, so you can replace this norm by this one, and so this is going to be less than some constant which depends on epsilon max over u in omega delta the epsilon u plus, well, some other constant which depends on epsilon. Okay, so
the claim is that this function f epsilon is contracted by the averaging operation.
yeah, exactly, and so, well, yeah, not,
You're
I mean, I will then say, yeah, then I define the function, well, the final thing you need to check is that if you define f, say, bar h equal to f epsilon h delta, this one is the function, this is going to be contracted by the operator. So this delta is, again, this one, it depends on the quadratic form and the linear map you've got. So this function here, contracted by 80. And then, yeah, then everything is working and you have your bounds. So, yeah, to show this, that once you have this kind of, these bounds that I've rubbed out, these bounds on the spherical averages, this kind of contraction on that, then you can, right, it's the argument that are used by Benoit and Kant. So they prove this kind of convexity properties for this function phi sub epsilon, and you can use, so in the same way they use those properties. So it basically relates things in the ith wedge and the jth wedge to something in the I minus jth wedge and the I plus jth wedge. So and you can use those properties. So they have something called the mother inequality. They derive some results from this, and you can use them and use them. Yeah, you basically use them to show this, and that's kind of the same as what they did. So the kind of thing that was different is, you just to replace the alpha function by this function, and then see that things are working out. So I don't know. I thought it was quite interesting. So that was kind of pretty much what I wanted to say.
Any questions?
So, Ollie, so when you had this f hat to the delta, was it? You were basically saying that all moments converge for the Ziegler transform?
I think. What do you mean?
So, on one of the board up there. You
So you have the original, so the analog of the Siegel transform. This,
Yes.
Yeah.
You have the supremum of all t
Yeah.
all t of the integral of f
Yeah.
hat to the delta is bounded. So
Mhm.
that will give you that all moments converge. Is that fair?
Yeah, possibly. Yeah.
Okay, but you never use the delta, right? You get some.
You need the delta to be bigger than
Right.
So it doesn't work if delta's too big. So I think you can take delta to be, it has to be, well, it works up to delta less than 2. Okay. The important thing is that you can prove it for some delta bigger than 1,
So
but you can't. You can. Oh, well, I don't know how to prove it if delta was 2.5.
I know where does delta come up here?
Just in this definition. Yeah, maybe I should stick a delta here.
Okay, so one of the convexity properties will fail when delta is too big. Is that it?
I think actually these spherical averages would fail. So these averages that I wrote down, where you're looking at the integral over k, kt to the delta less than c. Yeah, this would go wrong if. Well, so it depends. So that's actually interesting because this is kind of what goes wrong in the SO22 and SO21 case. It's kind of, well, there you're just using delta to be 1, and you can't prove this kind of result. You can prove it with a less than or equal than 1 here, but not for arbitrary c, and that means that there's some version of this kind of contraction lemma where you just have to stick a 1 over t in front, and then you have some version of that lemma which gives you that, in the end, gives you this extra log factor. So yeah, maybe in certain cases you could increase the delta, but because that's kind of to do with the dimension of so you've got this AT, and then you've got the dimension of the contracting space, the contraction of the shrinking space, and the fixed one. And it's to do with the ratios of the dimensions of those space in the wedge, which gives you the kind of delta here. That's kind of, so that's where the delta comes from. So yeah, maybe in some cases you could do it.
For the definition of the function phi epsilon, the power of 2 lambda of v is -1. Is that 1 over the norm of lambda or something like that?
So in your definition, yeah, you had these extra exponents, but it turned out you can set you can just choose them all to be 1, and it works. So yeah, So your definition was more general. I just said okay, let them all be 1.
So this non-divergent estimate is for any semi-simple group H. You have no assumption because at the very beginning H was some orthogonal.
Yeah, no. So that's it. I think it can hold in much more. So I haven't proved it in any more generality, but I think it's definitely possible to. And then you could get the
What
same.
is precisely your group H in your situation? Can you write?
Yeah. So I forgot to write that down actually. So because I had this condition rank Q restrict to M equals D minus S. Okay. So this was one of the conditions of the second theorem, and this implies that H is isomorphic to SO DQ with P at least 3, and the fact that the signature okay, so this condition, so that's why you need this condition in this case,
and
because
P prime plus 2 prime is smaller than D.
Yeah, P prime plus P, it's less than D. So
it's just included in upper left upper corner.
Equals D minus S. Yeah, after you conjugate it. Yeah.
Yes.
Yeah.
You think of it as being in a
Yeah, when you've conjugated everything, it is. Yeah, so it depends on, so it can be quite small. It's S. So in this I guess I didn't actually need to use that D was bigger than 2S anywhere. That doesn't come into it. So, but yeah, I think you should be able to replace in this thing H with some other reductive subgroup, and you should be able to replace G and gamma with just a semi-simple Lie group and lattice as well, and prove the similar sort of equidistribution statement.
question. Okay, so let's record it.